Okay, so differentiability. Differentiability. Differentiability is if a function has a derivative. Okay, so differentiation is the process of finding the derivative, right? That's what it's called. The differentiation's a verb. It means finding the derivative. So if I say differentiate, that means find the derivative, right? So differentiable means does something have a derivative? Okay, if it's differentiable, it has a derivative. If it's not differentiable, it means it doesn't have a derivative somewhere. Okay, so I can't find the derivative somewhere. Okay, that happens sometimes. Um, so this is kind of like continuity. When we talked about continuity, something's continuous or not continuous. It's kind of the same idea. So three conditions for something to be differentiable at a point. So for there to be a derivative at a point, first of all, it has to be continuous. Okay, so it has to be continuous. So there can't be any discontinuity, any type of discontinuity there. No sharp turns. I'll show you what sharp turns look like. And no vertical tangents. So what those mean is those are kind of like these guys. Okay. Um, this guy right here is a sharp turn. What do I mean by a sharp turn? Well, if the derivative is negative here, right? Because I'm decreasing. And then at this point here, so it's differentiable all the way till you get to this point right here. When you get to this point right here, then it's a sharp turn, right? That's not a smooth curve. It's a sharp turn. It's a point. It's a corner. We call it a corner. Okay. So we say that this guy right here, this guy is not differentiable at 0 because of this sharp turn. Another reason why is the derivative here is negative. The derivative here is positive. Well, what's the derivative here? Nothing. It doesn't exist. So that's why this one is not differentiable. This is a corner. So this is an example of a corner. A cusp point. Sometimes they're called cusp points. This one's a cusp point. Again, the derivative is negative here, and then it kind of comes to a point there, and then it changes direction and goes in the opposite direction. At 0 here, it's what we call a cusp point. It doesn't have a derivative at 0. It has a derivative here. I can find the derivative anywhere before 0 and anywhere after 0, but at 0, it doesn't have a derivative. Okay, so pretty much the rules for differentiability are this right here. If the derivative going in to a point, approaching a point, is the same as the derivative approaching from the other side, then it has a derivative, right? For example, I'll give you an example. That line. So let's say this point right here, right? The derivative here, as I approach this point, is the same as the derivative as I approach this point, right? It's got the same slope, right? It's got the same slope coming in as it does going out. So because of that, this one is differentiable at that point, okay? But these guys aren't. At this point right here, it's not differentiable at that point because before the derivative was negative, decreasing. And then at that point, it switches positive. So the derivative coming into that point is different than the derivative going out of that point. Because of that, we say at that red dot, it's not differentiable. Okay? Same thing here. The derivative here is negative, but at this point here, it changes. It changes. At that point, it changes from negative to positive at a cusp point. So because of that, we say it's not differentiable. Okay? So when you're checking differentiability, you're checking this guy right here. You're checking this guy. You're trying to see if the derivative going into the point from the left side is the same as the derivative coming from the other side. It's kind of like differentiability, or sorry, continuity. It's kind of like continuity. We talked about continuity. What makes something continuous? Well, if it's continuous, the limit as x approaches the function from the left has to be the same as the limit as x approaches that same point from the right, right? Which if those two are equal, then that means you have to have a limit at that point, and then that has to equal when I plug in that point, when I plug in that value. Okay? We checked that. Last chapter, that's what we did. The very last thing we did last chapter was continuity. The very last thing we're doing in this chapter is differentiability because they're very similar. Okay? The only difference with differentiability, so that's continuity. So for differentiability, it's very similar. Except we're using the derivative. We're using the derivative. So really you're saying the limit as x approaches c from the left, not for the function, for the derivative, is the same as the limit as it approaches from the positive side for the derivative, which is equal to the limit as x approaches c for the derivative, and then that has to equal. So it's the same rules, it's just instead of the function, you're plugging it into the derivative. Okay? That's the only thing with differentiability. So this guy, we used before because that was continuity. This guy is the new one, but it's almost identical. It's the same rules. The only difference is you're using its derivative instead of the function. Okay? So for the green guy, we plugged in the number, we plugged in whatever c was into the function. Now we're not doing that. We're plugging it into the derivative to check differentiability. Okay, but it's very similar rules. They set up very similar. Okay. Okay, so if a function is differentiable, so if you discover, hey, it's differentiable, then it also has to be continuous. Because they'll ask you that sometimes. On a test, they'll say, is this function differentiable and continuous? Well, if you verify that it's differentiable, then you don't have to verify that it's continuous. It has to be. Okay? If a function is continuous, it's not necessarily differentiable. So you have to check that. So if you start with continuity, you have to check differentiability next. So if I start with the green, checking the green, I have to go to the purple. But if I start with the purple and it checks out, green I don't have to do. Okay? If a function is not continuous, so if it fails the green, then I don't even need to check the purple because it can't work. Okay? So if you start with differentiability and it turns out, yes, it is differentiable, then you don't have to check the green. Okay? But if you start with the green and it checks out, you also have to check the purple. If you check the green and it doesn't check out, then you're done. Neither. Okay? So if you don't remember that, just check both. Check both and you'll be fine. Okay? But it's kind of like if it's differentiable, it's continuous. If it's not continuous, it's not differentiable. And if it's continuous, you have to check differentiability. Okay? So that's what we're going to do today. We're checking two things, continuity and differentiability. Luckily, continuity we've done before. That's not anything new. Okay? So let's look at number one. Let's look at number one. Okay, so number one, determine whether the function is differentiable, continuous, both, or neither? At the value where the rule for the function changes. Well, there's only one spot where there could be an issue with continuity and differentiability, right? There's only one spot. That's at 14, because that's where it changes, the function changes, right? Everything 14 and below, I use x squared plus 7x minus 20. Everything bigger than 14, I use 20x minus 6, okay? So what I'm going to do first is I'm going to check continuity. I'm going to check continuity first, because we've done that before. So start with something we know. So continuity. Well, first thing I have to do is check the limit as x approaches 14 from the left. And then I have to check the limit as x approaches 14 from the right. That, if both of those guys are equal, then that means the limit exists at that point. And then the last thing I have to do is plug in 14. So I need to figure out what values for each of those. We've done this before. This part we've done. This is not anything new. You've tested on it. Last test, this is what it was on. Okay. So if I want to check this guy here, what do I do? How do I check this? How do I do this guy? The first one. Input 14 on the first equation, because that's the less than, right? Good. So when I do that, when I input 14 on to the top equation, what do I get? Let's see, I get 14 squared minus 7 times 14 minus 20. 14 squared is 196. 7 times 14, 8, carry the 2, 98 minus 20. That's 98 minus 20 is 78. Mm-hmm. Oh, sorry, plus, yep, you're right. Okay, so I add those. So when I add those, I get 294, 294 minus 20, 274. Because we can't use calculator. These are no calculator questions. Okay. Now I'm going to do the same thing for the next guy. Plug 14 in, what do we get? $274. Then we are good. Yeah, because 20 times 14 is 280. 280 minus 6 is 274. Yeah. So that means the limit exists at 274. Okay. If I plug in 14, for f of 14, which one would I plug it into, the top or the bottom? The top. Yeah, the top, because the top is in equals. Top's in equals. I already did that. I did that earlier, so I don't need to do it again, but it's good to know. Okay, so it's continuous. It is continuous at 14. Check. So our list here says if it's continuous, then not necessarily differentiable. So I have to check differentiability. That's what I'm going to do next. Differentiability is the exact same thing. Differentiability is the exact same thing. The only difference is instead of the function, we use the oh, okay, gotcha. We use the derivative. Okay. Okay, so we make that differentiability. Okay, so we said the limit as x approaches 14 from the left for f prime should equal the limit as x approaches 14 from the right for f prime, which is equal to the limit as x approaches 14 for f prime, which is equal to f prime of 14. Here's the question. I need to find the derivative for differentiability. How do I find the derivative of a piecewise function? Like, how do I find f prime of x? That's my question. Yeah. Yeah, you find the derivative of the two. Yeah, you find the derivative of the two. So the derivative of the top would be 2x minus 7 when x is greater than or less than or equal to 14. And the bottom one would just be 20 when x is greater than 14. Okay. And then you go plug it in. So this guy here, we're going to plug into the top. So when I plug in 14 to the top, what do I get? 28 minus 7, 21. And then I plug it into the bottom. What do I get when I plug it into the bottom? Yes. Yes, that's the second time I did that. Yeah, no, you're right. Yep, plus 7. I don't know why I put minus. So it should be, what do we get? 28 plus 7 is 35. Okay. So 14 from the right. 14 from the right, what is that going to be? 20. Those don't equal. Those are not equal. I don't have to continue with the rest because for it to be differentiable, it has to be equal across the board, and it's not. So I'm done. So what's my answer? Well, let's see. Let me write it over here. We would say continuous f is continuous at x equals 14, but not differentiable. It's continuous at x equals 14, but it is not differentiable. And then it's always going to say justify your reasoning. Well, justification's right here. This is justification. Okay? This is what I see on tests, though. I see this on tests. People will put this. And they'll be like, that's justification. That's not justification. That's scratch work. Okay? That is scratch work. That's not justification. I know 35 doesn't equal 20. You don't have to be, my son's a kindergartner and he knows 35 doesn't equal 20. Okay? That's not justification. I know 274 equals 274 equals 274. I know that. That's just scratch work. Justification is that part there. That's justification. Okay? What is 274? What is 35? What is 20? That's what I need to see. That's your justification there. Okay? This is just your conclusion. That's just your conclusion or your interpretation. Okay? All right. So I want you to do number 2 now. Do number 2 on your own and see what you get. Okay. So the limit of as f approaches -2 from the left, I'm going to plug in the top. And when I do that, -2 squared, 4, 4 minus 22 is negative 18. We get 6. Yep, okay. And then I plug it in here, negative 2, to the second one, and I get also 6, which means that equals 6, which means, and then if you plug in negative 2 for f of negative 2, you would plug it into the top because that one has the equals, and we've already done that. So we get, oops, not negative 2, we get 6. Continuous at negative 2. Actually, continuous everywhere. But they wanted us to check at negative 2. Okay, so that means we have to go to differentiability. So I'm going to do the same thing, except now instead of the function, I'm going to go to its derivative. The limit as x approaches negative 2 from the right, f prime of x. The limit as x approaches negative 2, f prime, and then f prime of negative 2. Okay, so I need to find f prime first. So it's 2x plus 11 and 7. Okay, so when I plug in negative 2 to the top derivative, 2x plus 11, I get 7. When I plug in negative 2 to the bottom, I still get 7 because it's just a constant. That means that's 7, and that's 7 as well. So we would say this function is continuous and differentiable. F is continuous and differentiable at x equals negative 2, really everywhere, because that's the only spot where it could have been not continuous or not differentiable. Because before 2, at 2, and before 2, it's a parabola. Those don't have any discontinuity. And then below it is linear. Okay. All right, so now let's go to example number 3. Okay, example number 3 is exactly the same, but they want us to say, hey, determine the values of a and b, which would result in it being differentiable. So a and b are numbers, values. They're not variables, okay? So it's saying it is differentiable at negative 2. What are a and b going to be to make it differentiable? Okay, so let's find. So you've done this before, but with continuity. I think you had one like this on your last test, but with continuity, where you had to find the differentiability. It's the same thing. They have to all be equal. They have to all be equal. The limit as x approaches negative 2 from the left for f prime has to be equal to the limit as x approaches negative 2 from the right. X approaches negative 2 for f prime of x, and f prime of negative 2. Okay, so we need to find a derivative. So the derivative of the top, 3ax plus 3. What would the derivative be there? 3ax plus 3. 3a, good. 3a, because 3a is the coefficient. So it's 3a. And the bottom, we would need to move the 2 to the front, so it's 4b x minus 1. Okay. Okay, do the same thing. Plug in -2. What do you get? What do we get when we plug in -2? So when I plug in -2 from the left for the derivative, what do I get? 3a. Yeah, I don't get -6. I do not get -6 because I don't plug in -2 for a. So I get 3a. Okay. Then I plug in -2 to the other one. I get -8b minus 1. So that means this. So these are differentiable. It said they are differentiable. It didn't say they want us to check differentiability. It says being differentiable. So that means this has to equal this. Okay, so I'm going to leave this one blank for right now because this is essentially just this. And then if I plug in -2 for f prime, I'm going to get 3a again. I already have 3a. So essentially I have this. Okay, so essentially I have this. I have, write this down over here. 3a equals -8b minus 1. How do I solve for a and b? Okay, so for systems, we have one equation. I need two equations for systems. I could do that. Systems could work, but I need two equations, right? That's what I did last chapter. So where do I get the other equation from?
So set like one variable equal to like the whole equation, and then you can enter that value into the set of equation, like instead of like a variable, I guess.
So yeah, you're right. You're absolutely right. We're going to do that, but we need a second equation. Where do we get that second equation from? I need another equation to be able to do those things. Where do I get it from? Not the original. You're close. Not the derivative. Read the first one. Read the first bullet point. What does the first bullet point say? Mhm. So we know it's differentiable because they told us it's differentiable at -2. It said. So then it must be continuous. That's where I'm going to find my second equation. I know it's continuous. I know all of those guys should equal each other, not only for differentiability, I know they should equal each other for continuity as well. Okay, so I'm going to do the same thing, continuity. I know they're all going to equal each other. They have to. If it's differentiable, they're going to have to equal each other. with continuity. They're all going to have to equal each other using continuity as well. Not f prime, just there we go. Okay. What do I get? What do I get when I plug in -2? Where am I plugging it into? Where am I plugging this guy into? Yeah, the, which one though? I have two equations. The original, yeah. This is the original. So I plug it into the top of the original, plug it in for x, and I get -6a plus 3. Because I plug it in for x. Okay, that has to equal, plug in -2 to the bottom. So I get 8b plus, no, -1. So -2 squared is 4 times 2, 8b. And then I plug in -2, that's +2 minus 3. Nope. Yeah, the -1. Yeah, that's right. Okay. That means both of those guys are that. And if I plug in -2, I get -6a plus 3. There's my next equation. -6a plus 3 equals 8b minus 1. Okay, how do I solve for a and b? We did this last chapter. I have my two equations. How do I use them to solve for either a or b? Huh? Okay, so what does that mean? So I have, systems means two equations, and I have two equations. Let me write them down. -6a plus 3, 8b minus 1. So I have two equations. They're both linear because there's no exponents. Systems of equations. How do I solve systems of equations? What do I do? What did I do last semester? Not last chapter. What did I do last chapter? Yes, so I need to do that. When we use elimination, like we did last chapter, what form do they have to be in? What form do both of these guys have to be in? To use elimination. Because right now they're in no form. Which form do they have to be in? Not everything. Which form? There's three forms. Which form do they need to be in to use elimination? Standard form, where the variables need to be on one side and the guy without a variable needs to be on the other. So the top one, I would add 8b to both sides, and I get 3a plus 8b equals -1. The bottom guy, I need to subtract 8b from both sides, so I'd get -6a plus, or sorry, minus 8b. Then I would subtract 3 from both sides, and I get -4. All I did was add 8b to both sides, and then subtract 8b, and minus 3. That's all I did. Okay, add straight down. I get negative 3a. B's go away. Was this negative 5? Divide by negative 3. I get a equals 5/3. A equals 5/3. Okay. How do I get B now? Yep, plug them into any of these equations. This guy or this guy. Doesn't matter, whichever one you want to. You'll get the same answer for both. So I'll use the top. So 3 times 5/3 plus 8b equals negative 1. Those cancel out. I get 5 plus 8b equals negative 1. Subtract 5 from both sides. I get 8b equals negative 6. I divide by 8. B equals negative 3/4. Okay. We've done all of that before, just with just continuity though. So you've done all that before. These are prime for free response questions. Prime for free response questions. They like these types of questions for free response questions. So I'm going to give you another one on your own. I'm going to give you number 4 to do on your own. Okay? Number 4 to do on your own. I'll give you some time to do